Yeah, you got to do this term by term. So you're going to use, well, first of all, what's the derivative of a constant? Always.
0.
Okay. Now what's the derivative of minus x squared using the power rule?
Negative 2x.
And now, because I'm using F notation and not Y, I can do this. So what's that equal
to? 6.
What's F prime of 0 equal to?
F prime of 0.
The second part of that question.
So would that be 0 as well?
Well, that would be 0. The first one, remember, was
0. I mean, yeah.
Yeah.
Sorry.
And what's F prime of 1?
Negative 2.
Yep. It's as simple as that. Now,
Okay, and apparently we have to like find something about corners or something on number 38. Or let me send you a picture of that one. One moment.
okay. I'm a little puzzled at question number 2 as to why they use capital F. Because in calculus, capital F is generally the antiderivative, kind of what it means. But I suppose it doesn't really matter. You certainly haven't gotten to antiderivatives yet. Surprised they would confuse the issue by using a capital F, because in a month's time, that's going to have a whole different meaning.
Okay, I'm about to send you a picture. I'm going to send you 2 pictures, actually.
Okay. While we're waiting for those, shall we do more on this page here?
Yeah, we can do number 2. Or let's do number 3 because that one seems a little bit more difficult.
It is. It's not really difficult. You'll find these are amazingly easy, even when you get to the product rule and the quotient rule. Chain rule can be a little tough, but so here we have a function g of t. That means we have a function g that's going to have nothing but t's on the other side. Now, if I write it like they've given it to us, I cannot apply the power rule immediately. I have to write it like this. Means the same thing, right? But I have to have t in the numerator. I can't apply the power rule if t is in the denominator. But once I write it like this, now what's g prime of t?
Negative 2t.
Negative 2t to what? Remember, you always subtract 1 when you're doing
negative 3.
Correct.
Negative 3. Yeah.
You do get to integral calculus, which is finding antiderivatives. It's the opposite. You always add 1. But as long as you're doing differential calculus, you're always going to subtract 1 from that. And that ends up, now they usually want you to put it with positive exponents. In other words, put it back into the format that they kind of gave it to you. So that's g prime of t. Now what's g prime of minus 1?
Would that be negative 2?
No. G prime of minus 1. If you try to do the whole problem at once, you can make a mistake quite easily.
Okay.
What's negative,
so
negative 1 cubed?
Oh, okay.
So
that would be negative 1.
And then what's negative 2 divided by negative 1?
Just 2.
Positive 2. Okay. And I'm sure you can figure out g prime of 2. However, what's g prime of root 3?
So root 3 to the third power, would that cancel that out?
Hold on. Well, first of all, spell it out. In other words, don't try to answer it all in one question. Do this. It's minus 2 divided by root 3 cubed. Okay? Now, root 3 cubed can be simplified. Remember what it is. It's root 3 times root 3 times root 3. What's that simplified to?
Root 3 times root 3 times root 3 cubed.
No, that's what cubed means. Is I'm multiplying root 3 times itself.
That'd be root 3. That'd be root 3.
Well, hold on. This is what we're doing. What's that?
That'd be 3. Oh, 3 root 3.
There you go. Now, are they sticklers for rationalization? For rationalizing denominators?
Not exactly in this case, because he says in calculus it's fine or something like that.
Well, make sure that that's true with your teacher.
Okay.
I like that myself. I don't think we should rationalize denominators, to be honest with you. I don't know why we do it. In trig, it's far superior to not rationalize denominators. But by the strict convention of mathematics, you're supposed to. And if you have a teacher who's a stickler for it, you may not accept this answer. You might lose a point if you were to put that answer on there. And of course, you rationalize it by multiplying top and bottom by root 3. If you had to rationalize it. All right, let's have a look at the other document that you sent. Which one first?
Let's do the bottom one, which is 31.
I have a left and a right.
Or the left one, I believe.
Can you see it barely on my screen?
Right. Yep, I believe the left one.
All right. That one?
Correct, 31.
All right. You cannot differentiate around corners or cusps. In other words, if I have a smooth curve, I can differentiate at every single point of that curve. Every one. But if I have a curve that looks like this, I cannot differentiate at that point right there. And what that means is I cannot find the slope of the tangent line. Right? That's what differentiation is. So notice that I could guess the slope of the tangent line might be that, but gosh, I could also guess that. You really can't figure it out. And mathematically speaking, that means you can't differentiate it. Not all functions at all points can be differentiated. So you're going to get an awful lot of questions that say a function is differentiable at all points on its domain, but not all are. In other words, that's a key condition for being able to take the second derivative. But so what points is f prime not defined in this picture?
It looks like negative infinity to negative 4.
Hold on. This entire function only goes from -4 to 6 on the domain.
Okay.
So what points is it not differentiable?
It looks like it's continuous throughout the whole thing.
Well, what do we have going on right there? That's a
Corner.
That's a corner or a cusp.
Okay.
Not going to be differentiable at that point. Now,
Okay.
at this point down here, I can find the slope of the tangent line. It's the same as the slope of this whole line right here. So it is differentiable from x minus 4 to x 0, but it's not differentiable at x equals 0. What's the next point that it's not differentiable at?
6, 2.
Oh, how about this where x is 1? That's another corner. In other words, what you're looking for is all the corners.
Okay, so each corners are not differentiable.
Except the first and the last. Those are. Those aren't really corners. That's just an endpoint. Okay? But there's 3 corners. There's x equals 0, there's x equal 1, and there's x equal 4, where the function is not, the first derivative is not defined. And it says give reasons for your answer because it's a corner or a cusp. There are actually far more complicated reasons that you could use the limit quotient definition to prove that it's not differentiable, because the limit of the slope from the left is not the same as the limit of the slope from the right. That's the more mathematical way to prove that it's not differentiable at corners or cusps. But generally, that's enough of an explanation. Graph the derivative of f. Well, let's graph it. It's easy to do. Okay. In other words, instead of y prime, I'm going to label, instead of y, I'm going to label it y prime. Okay.
Okay.
What is the slope from minus 4 to 0?
Would I have to do y2 minus 1?
Yeah, what's the slope of that line? It's rise over run. Don't worry about y2 minus y1. What's the rise? What's the run? It's real easy.
Okay, well it runs 4 and it rises 2.
Always do rise first, because it's the
Okay, so 4, okay.
Okay.
So 2 over 4, so 1/2.
Okay, is it positive or negative?
Positive.
Okay, so from minus 4 to 0, I have a flat line at 1/2. What's the slope from 0 to 1?
That would be -2 and 1.
What's the slope of that second part of the line? Remember what derivative is. Derivative is slope, always. Make sure you always remember those two words mean the same thing. So
would it be -2?
Well, what's the rise over the run of that part?
Because I see that you have to go down, -4.
Correct.
Okay, got it.
So now, and incidentally, that is an open dot right there because it's not differentiable at x equals 0.
Okay.
Closed dot right there. But between 0 and 1, I'm going to be at -4 the whole way. Again, open dot there, open dot there. Now, between 1 and 4, what is the slope?
I think it would be 3, just 3.
It's the slope of a horizontal line.
Actually, would it be 0 because there is no rise, just a run?
Exactly. The slopes of all horizontal lines are 0. What's the slope of a vertical line?
However, how it goes.
Undefined. Basically infinite. But you're not going to run into a whole lot of vertical lines because calculus is all about manipulating functions. And in a function, you never have a vertical line. Can't. Otherwise, it wouldn't be a function. So between 1 and 4, it's not defined at 1. It's not defined at 4. And the slope is 0. Okay? Now, between 4 and 6, what is the slope?
That would be it would be 4 over 2, and that would be 2.
Correct. See why you're really almost better off not going through the y sub 2 minus y sub 1 over the x sub 2 minus x sub 1. When you have a problem like this, it's really easy to look at the graph and figure out that, well, the rise there is 4, the run is 2, and I'm looking at a positive slope, so I know it's plus 2.
Mm-hmm.
And it's open there and closed there because it is defined at x equals 6. So
okay.
There is the graph. Yeah, the graph should show a step function. Well, I guess it does show a step function, doesn't it? A weird brand of a step function, but okay. What else, Taylor?
On the next picture I sent you, number 38.
Okay, here's the part that when I said that there was a more sophisticated mathematical way of doing it, this is the way. In other words, that's what they want you to do on both 37 and 38. In other words, we can talk about cusps and corners all you want, but you need to be able to mathematically show that the derivative produces two different derivatives depending on whether you approach that point from the right or the left. Okay? Now, compute the right hand and left hand derivatives. At this point that I'm pointing at here, P in 38, what's the derivative from the left?
Oh yeah, that's a slope, so it would be 0.
What's the derivative from the right?
That's a good question because it's like slanted.
What's the equation of that line? Y equal 2x. What's the 2? That's n. That's n. In other words, it's in y equal mx plus b format.
Okay.
So
the slope is y equals mx plus b.
Well, so what we care about is the m. I don't care about the b, but the m is 2. That 2 is in front of the x. That makes it the m. Okay, so the slope from the right is 2. Since they are not the same, then it is not differentiable at that point. For it to be differentiable at a point, the slopes have got to be the same from the right and the left. Now, let's look at 37 just so I can illustrate my point. If I want the slope from the left, what's the first derivative of this function?
1.
Use the power rule. What's the first?
Oh, okay. So 2x.
Okay. What's its value at this point right here? In other words, what's the slope of the tangent line right before 0?
Right before 0.
Well, it's not differentiable at 0. But let's talk about it at 0. If what would the slope of the tangent line be? If the derivative is 2x, plug in 0 for x, what's its slope?
0.
Okay. So the derivative from the left is 0. What's the derivative from the right? Take the derivative of this function, y equal x.
So would that be 0 as well?
No. If it was, then it would be differentiable at point P.
Got it. So would that just be 1 because it's invisible?
Just 1. In other words, it's the coefficient. When you're taking the derivative of a linear variable like x, in other words, the derivative of 7x is 7. The derivative of 10x is 10. The derivative of 1x is 1. So we've got our derivative equal plus 1 from the right, but it's equal to 0 from the left. Since they're not the same, the thing is not differentiable at that point. So they do not even use the word cusps or corners in your school. Although I've never seen a calculus book that doesn't use those terms. And it's pretty easy to recognize a cusp or a corner. But technically, this is the way to prove that it's not differentiable at this P or this P over here. In other words, I don't have to know that that's a cusp or a corner. I just got to differentiate it from the right and the left, and if the two are not the same, then it's not differentiable at that point.
Okay.
Okay. What else? We've got 7 minutes here. Unfortunately, I don't have any extra time. I've got a 6:30 that I got to go to, but
Okay.
we'll cover in the next 7 minutes. On this page,
okay, I'll send you another
what's that?
I'll send you another photo really quickly.
Okay.
And it just got sent.
Must be heavy internet traffic. That's interesting.
Possibly.
I bet it is. Well, I'll bet it's as bad right now as it is at any time during the day. Well, seriously, because everybody gets home from work. And
True.
it takes a little longer for stuff to get to me when the general internet is bogged down. Which one?
39.
Okay, I was going to suggest we do that. What's the derivative from the left at point P?
That looks like it would be, so at point P.
At 1, 1. First of all, you have to differentiate the function.
Okay.
The derivative of that. Radical signs do not work well in calculus. Every time you see a radical sign, convert it to an exponent, always.
Next to the half.
Because once you got a fractional exponent, now you can apply the power rule. So what's y prime?
1/2 x to the negative 1/2.
Now, what is y prime at this point, which is x equal 1? See what I'm doing? In other words, I'm trying to figure out what the derivative is at that point. And I'm checking it from the left-hand side first.
Okay, so I'd have to plug that into there?
Sure. Whenever you're evaluating a function and you got something other than x in the parentheses, that means you plug whatever is in there in for x. What do I get?
Okay. 1/2 of 1 to the negative 1/2.
Which is 1/2.
Okay.
In other words, 1 to any exponent is 1. Okay?
Yeah,
Now let's look at the function from the right. And this time, this is the equation from the right.
Even though it's a negative 1/2?
No, it's positive. Remember, negative exponents do not have anything to do with being negative. A negative exponent merely means that that is in the bottom, like that. That's what it means. So there's nothing negative about anything there. When we plug in 1, we're taking the square root of 1, which is 1, and then we're multiplying it by 2. Okay. Now, in looking at this picture coming from the right, what is y prime?
2.
So what is y prime evaluated at that point 1, where x is 1?
So that would be 1.
No. Plug in 1 for x. Notice there is no x. It's 2.
What about the -1 in the back?
That disappears when you took the derivative. Remember, the derivative of a constant is
0. Oh yeah, it's always 0.
But not only that, they gave it to us in mx plus b format. So we really didn't even need to take the derivative. We just needed to know that that was m. That's the slope, too. Okay? But I wanted to be consistent. You're always taking the derivative of each side. But so what we got is from the right, that was the derivative. This is the derivative from the left. Since they are not the same, it is not differentiable at point P.
Okay.
And use the same logic for every one of these. In other words, slope on 40, the slope from the left is +1. On the slope from the right is whatever the derivative of that is, which is -1 over x squared. So it's -1 from the right, it's +1 from the left. That's not the same, doesn't exist.
Okay. Thank you.
You're welcome. Talk to you next time, Taylor. Bye-bye.
Sounds good. Have a good night.